Well, my main interest here is to privilege physics over cosmology, because I think physics is more fundamental. And I want to put that first. I want to start right at the beginning with Einstein's special and general theories of relativity. And there are certain problematic aspects of these theories. It's not that they yield incorrect results. We know they don't. They yield largely correct results. It's the interpretations of them that worry me. And the way people look at them, other than as mathematical theories, the physical interpretations. And these interpretations have had an impact on both physics and cosmology. If we take special relativity, the problematic aspect, which is one of Roggero's points, is that it is assumed to apply outside of the exterior application to point particles and waves in vacuum, and that it's assumed to apply in interiors and in media, especially anisotropic ones. And as soon as we have a medium or extended object, it doesn't apply in the same way. And one of the possibilities is that the velocity of light is not the maximum attainable speed. I won't be talking a lot about that, but that would have an impact on cosmology. In the case of general relativity, the cosmological impact is much more direct. And one of this stems right back to 1919 when Eddington presented the theory, and he promoted the theory as a revolutionary development. And it was making a significant break from everything that had happened before it. And I think that was not a good thing, really. It should have been presented in the way other theories have presented, as a natural development of previous theories. And that was never done properly. It was assumed that there was a big cut-off, there was a revolutionary change, and that we had to think totally differently. And I think that was completely wrong. That is not the case. So the new understanding was that the gravitational force was entirely superseded by some sort of geometry, a Riemannian geometry, and we could overthrow all our previous ideas and institute this geometry instead. And the revolutionary rhetoric also led to a bit of an Einstein-type religion. So if you discussed this special relativity or general relativity in any way in which you were critical in any aspect, it created automatic hostility, and it still does. Though we know perfectly well, and it's often said, that neither theory is completely the final word on its subject. It can't be. We know that they don't completely fit in with other aspects of physics, that there is some adjustment to be done somewhere. And no other aspect of physics has ever got to that status, or certainly no aspect of recent physics has. Everything has to be open to question and development. So if we put some portion of physics as untouchable, then we will fail at the foundational level to understand the real issues. Now, Cartan later showed that any physical field theory, including Newtonian gravity, could be represented by geometry, could be represented by space-time curvature and that kind of thing. And we've never really accepted that the curvature concept is just a representation. It's not a revolutionary change. It doesn't say that curvature is everything and nothing else matters. It's just a representation. And as Cartan showed, it could be used to represent other field theories. And I think people have not gone back to their Newton to find out how he did it. And after Hyde had done the work I'm going to mention later in this talk, I actually went back to Newton's Principia and looked at the way he actually did his calculations. And it's not at all like people think. For example, the two-body problem is very straightforward. You get the elliptical solution, elliptical orbit, inverse square law of force, quite straightforward at one of the foci. However, once you get a perturbing body, for example, let's take the Earth-Moon-Sun system, which is what he looked at. As soon as you got the Sun involved, as well as the Earth and the Moon, you get complications which are too difficult to solve analytically. And he introduced a perturbation method to do it. But what kind of perturbation method did he do? And I don't think this is all that well known. If you look at what he did was to take an elliptical orbit as the standard. It was going to still be an elliptical orbit after the perturbation theory. What he was going to do is change the coordinate system. In other words, that it would still be an ellipse in that new coordinate system. And that would be a varying coordinate system. So we had a varying space and time coordinate system in which there would be an ellipse preserved. Now, that isn't at all what people think he did, but that's what he actually did. And to me, that's not very significantly different from using curved space-time concepts of general relativity. You're using the same basic principle, you're changing the coordinate system. And if we'd accepted that general relativity was a new change in the coordinate system to allow for the finite velocity of light, then I think we would have understood it better. And in fact, Newton could have done that as well, because he knew perfectly well that the velocity of light was finite. He knew that it affected astronomical observations, because that's how it was discovered by Römer. It affected the astronomical observations of the moons of Jupiter. So we knew that finite velocity of light was important when you were actually making observations. So he could have done that, and the reason why he didn't is because observation at that time was too imprecise for it to be of any practical value. But he knew that it could have been done. He was aware that it could have been done. And if you were to take this to its limit, you would also have to say, is light affected by the gravitational field? It's not just the fact that observation is affected, but is the velocity of light affected by the gravitational field? And he certainly thought it was. So additional change just for observation would have had to be made for light. Nothing to do with whether gravity was transmitted at light. There would have had to be a change for that. So in that coordinate system, an extra term would have had to be added just for that. And that term would have had to depend on gravity, because he knew, and we know, that gravity affects light. And so subsequent investigators did, in fact, start to work on these things, and they got to a certain degree of credibility with their explanations. Now, I'm not concerned with whether they were successful or not, and they were partially successful, but the fact is that correct results could have been derived in that way. I think the important aspect is to realize that nothing in general relativity requires to believe that there's anything other than Euclidean space. But we could easily use different coordinate systems that aren't purely Cartesian. That would have been quite standard. And now we've got mainstream evidence which shows that the universe is Euclidean. That's been around for more than 10 years, that the evidence that says it is. Now, this was not fully understood in 1919. Cosmologists also, when they're confronted by a new problem, they tended to also indulge in revolutionary rhetoric and expect solutions that didn't agree with previous ones. And so that whole culture developed in that way, which was not a good thing. Now, if one looks at general relativity as it is, as one actually works out anything in it, at some point you have to introduce the Newtonian potential. You have to say this curvature term has to be replaced by GM over R, otherwise we can't make any physical sense of it. It's not as though it's something completely separate from that. And soon after that, Alexander Friedman's three solutions for different densities, expanding, contracting, and stationary, they're certainly true, but they're not really directly connected with general relativity. It's only the Newtonian component that matters. It's where the density is, it's what the density is that matters. It doesn't matter about the curvature at all. So it's nothing to do with any special aspect of general relativity that we get three different solutions of the field equations. And that's those solutions. So let's look at now cosmology. After this, 10 years after this revolution that was proclaimed in 1919. And of course we start with Hubble's law, redshift versus distance. And redshift is interpreted as a Doppler effect quite reasonably, as you'd expect, suggesting galaxies were moving away. And then Lemaitre came up with the primal atom, as he called it, the primal atom.
Can you repeat, please?
Lemaitre came up with the primal atom, the Big Bang theory, from an atom, or from a primal point. And remember that Lemaitre was in fact a priest. It was in fact natural for him to look for an abrupt beginning of the universe. Zwicky, of course, suggested the tired light explanation due to scattering, but nobody took too much notice of that. And that's the Hubble redshift. Now, we've indicated already that expanding universe equations are nothing to do with general relativity in principle. If one looks at the expanding universe equations, they're just absolutely pure standard Newtonian physics, nothing to do with general relativity at all. And Milne and McRae showed that in 1934. However, it seemed to be revolutionary, so that was what the idea was. Now, the Big Bang theory seemed to be the only one available from 1930 up till 1948, when one got the so-called steady-state theory of Bondi, Gould, and Hoyle. And this steady-state theory was that the universe kept in a steady condition as long as you kept creating matter as it expanded. And so it wasn't really a steady-state theory at all, because there was a continual change. And you got the universe was still expanding. And this was always presented as the alternative, and people still say, you don't believe in the Big Bang theory, you must believe in the steady-state theory then, as though it's one or the other, black and white. And also, it collared the name. The steady-state theory took over the name. And so anything that didn't go for expansion must be the steady-state theory, because that's the only theory that's steady-state. It's already monopolized the name. And in fact, it's become a straw man. So it's usefully occupying the alternative ground. So you've either got to believe in the Big Bang theory, or you've got to go in for that nonsense called the steady-state theory. And nobody's really thought about non-expansionary theories. I'm not saying expansionary theory is incorrect. I'm not going to say that. I'm talking about separating physics from cosmology. I want a separate structure for physics from the structure of cosmology. And then people can decide these things on a more rational basis. So in 1965, Penzias and Wilson famously detected the microwave background radiation, which was immediately interpreted as evidence for the Big Bang theory. And they were awarded the Nobel Prize within 2 years, which was incredibly quick for a discovery of that kind. And it's, I don't wish to make any special comment about that, but it was a very quick award. Now, it was claimed that Gamow had predicted it from the Big Bang, but Gamow's prediction was nothing like the correct value for the temperature. It was 50K, if I remember rightly. And in fact, Eddington had actually calculated the temperature based on the density of starlight back in 1926, and he got 3.2K. Several people had calculated it earlier. The most refined calculation up till that time was Eddington's, and he got something pretty close. Now, the theory that came out of this was that the theory that seems to have emerged by now, but wasn't the original theory. It wasn't the original theory. Is that originally there was an idea that there was a rapid expansion from a point of infinite density and temperature, and that it created space and it created time. And then following that, one fitted the data to develop a history of the universe. However, people have tended to give the impression that that fit is also extra evidence, which it isn't. The only evidence is the original evidence. There's no evidence really based on abundance of elements. All you're saying is that they fit in with it. That's a fair enough thing to do, but it's not extra evidence. The singularity caused problems because there were people in the 60s who thought it was a kind of reverse black hole. So black holes are collapsing into a point. This is an expansion out of a point. And in fact, it's not possible because that is going back to the medieval idea that there is one point that's special. It was also generally thought that the universe was finite and curved. In the 60s, that was completely standard. Completely standard. Nobody believed in the kind of universe we have today at all. But the modern version of Big Bang singularity is not that at all. It's been changed. But it's been subtly changed in such a way as we get the impression this was always the theory, but it wasn't. The theory now is that there's expansion from all of space. There's an expansion from the infinite space, even though this space has to be created. Now, it's a sort of concept that we just can't get hold of. I'm not saying it's wrong because we can't get hold of it. It may be that there are things that we will never be able to get hold of fundamentally that are still true. And the infinite density became a finite one, reducing over time. And how did this happen? Well, where did this come from? Well, it was quantum fluctuation. That's the general feeling. But that left problems with uniformity and isotropy, because relatively slight fluctuations would have produced massive non-uniformities and anisotropies. It should be anisotropies. And they couldn't explain the smoothness of the continuous cosmic microwave background radiation. Now, if we look at it, there's only two pieces of evidence that really fit the picture. That not fit the picture, but that demand the picture. There's the redshift and the background radiation. And they're not actually connected very strongly in a mathematical theory. The second is not a strong derivation from the first. We can't say that we've got a picture in which it's inconceivable that anything else could happen. And the original Big Bang theory had two major problems, one which required a drastic solution soon after. There was the flatness problem from the metric for expanding space, the Freeman, I don't know what the L is now, Robertson-Walker metric. Small departures from critical density with the Planck time grow with time to big ones, and we don't see those big variations. And even after a few minutes, which is the time of nuclear synthesis, the universe density must have been within 1/10⁻14 of the critical value, so it must have happened very quickly. The other problem was the horizon problem. If no information can travel faster than light, and the universe is 13.7 billion years old, then certain regions couldn't be in communication. I think I'll leave out the last point. Well, I don't think anybody, even the most avid and convinced supporter of the Big Bang theory, is that comfortable with the solution that we have now. It's definitely ad hoc and it's unsatisfactory. A very short period of rapid and exponential inflation has caused the flat distribution and a universe exactly at the critical density. And later observation has shown that that universe is flat and Euclidean and at the critical density to a very high degree of precision. And I don't think anybody's all that happy with that. So you have a homogeneous and isotropic scalar field dominating the universe at some early period, and that's before you get the formation of protons and things, baryogenesis. In that period, there's an exponential expansion, so regions that once were widely separated very quickly have a causal contact. And quantum fluctuations in the early universe are responsible for observed structures now. And I remember when the fluctuations in the microwave background radiation were announced on news for the first time. And it must have been a bit like the Eddington announcement in 1919, the way it was done. It's not normal to make, it wasn't normal then to make such big announcements about scientific discoveries on the news. They didn't normally get onto the news. So somebody must have had good access to the news media. So during the inflation, then the space-time expansion is so rapid that it quickly loses all curvature and the density becomes critical, so it becomes flat. So that's the way it's done, and that's the standard picture that you see everywhere of what happened. You can see the inflation bit, and then suddenly you get flatness. There were some difficult aspects to this as well. The assumption has always been that there's zero matter, but there's energy. And if you've got energy, then the Big Bang can't start from nothing. And that's a bit problematic if it doesn't start from nothing. People say it starts from nothing. It doesn't start from nothing. It starts from some sort of energy density, maybe infinite. But that's a strange thing. And then it splits into almost equal amounts of matter and antimatter, but matter's slightly predominant. And the antimatter's annihilated, leaving a small amount of matter. There's a lot of questions over that as well. Why the asymmetry at all? Why is there a little bit more of one than the other? And also, even if you do believe in that, then CP violation, which is the thing that has often been claimed as the thing responsible, doesn't explain it. Because CP violation is mesonic. It's about mesons, which are not different amounts of matter and antimatter. They're the same amount. A meson is made up of one piece of matter and one piece of antimatter, and it's not different amounts. And it doesn't change the relation at all. So the way we've observed it so far cannot actually explain it. Then we have new problems arise. So dark matter, old problem. Zwicky again is the first to observe it in the 1930s, but nobody again takes much notice of it until after the Big Bang theory as established in the 1960s. So Zwicky found the dynamics of clusters of galaxies seem to require extra mass. And then subsequently the same problem was seen in individual spiral galaxies. Interestingly, however, if you solve the problem for galaxies, that solution doesn't solve the problem for clusters of galaxies. It turns out to be different. You can't add up all the galaxies, dark matter, and get the clusters to make sense. So that's an extra problem. There's two problems at least. So here, this is a well-known problem in spiral galaxies where the curves flatten and they should decay, as in where it says luminous, instead of flattening out at the top. So that's that problem. And if dark matter exists, it's certainly very strange. I've talked a lot about it with my colleagues who are experimental particle physicists, and they can't really think of anything that really fits the bill that they could have seen or are likely to see. There are some high speculations about it, but it doesn't really have the feel of matter as we understand it. It couples only to gravitational fields. That's a very odd kind of matter. And why should it exist only outside spiral galaxies, not in them? And what about other types of galaxy that aren't spiral? Why isn't the dark matter there? So it's a major problem. However, the standard picture is that we have a big problem. There's 74% dark energy, or something like that, 20-odd% dark matter, and about 4% of ordinary matter. Dark energy, of course, as you know, came from the observations of using supernovas as standard candles, and appeared to show an outward acceleration in the Hubble redshift. So mathematically, it had the same form as Einstein's cosmological constant, but it wasn't anything to do with preventing the universe from collapsing. It was actually making it go outwards, so it wasn't actually quite the same thing. But famously, this is not even wrong. And it's not even wrong, because it's as wrong as it could be, because it's 120-odd orders of magnitude wrong. And you cannot get wronger than that. If you follow what Seth Lloyd said about the number of bit flips that could happen, so in other words, the number of possible quantum events that could conceivably happen in the Hubble universe, it's something like 10 to the 123. So if every single conceivable quantum event happened, then it still would not be enough to explain the discrepancy of the dark energy. And that's the dark energy curve, as you've probably seen many times, and that's something else. Yeah? Now, so the current state of cosmology is that we've never quite had a Big Bang theory. We've got a Big Bang concept. We've got an idea that there was a Big Bang, but we can't actually quite pin it down to anything that makes total sense. It's a number of bolt-on quick-fix remedies, and there's some problems without any answers, like dark energy and dark matter. And it's never actually made a successful prediction. It's got a terrible record as a predictor. Most theories will actually come up with a good prediction, and people say, well, that's good, you know, but at least that proves that the theory's switched on in some way. But this one has got the world's worst record for predictions. Yeah. So it's had to change from a point-like origin, primal atom, to an infinite one. It's had to change from a finite universe to an infinite flat one. It's had to incorporate dark matter. It's had to propose a special period. Everything coincidentally seems to point to the fact that the critical density happens now. And it's also something I haven't mentioned. It's got major problems with entropy, because there isn't enough entropy to explain the universe from the start to what we've got now. I think we've got more entropy than we could have had in the early universe, and we can't explain where we got it from. Okay, so there are clearly many problems. And I'm saying that this is something that we want to separate physics from. Cosmology has to speculate, it's got no option, and I have no objection to that whatsoever. But we shouldn't say it's the same as mainstream science, it isn't. And it's sort of excluded other possible approaches. I don't know, these are naive questions. Somebody may know the answer to this. So if the Big Bang happened everywhere at once, where was where? So why do we observe expansion at all? If every point of space is expanding, why don't atoms expand? I know I've never got round that one. Never got round that one. Why? So if every part of space is expanding, we shouldn't observe it. That's the nature of space. Why is it only gravity that seems to be involved and not other forces? And then we've got faster than light expansion beyond the Hubble radius, and that's considered perfectly all right. Well, maybe it is all right, but I'm just saying these are questions that we've got to ask. We can't use cosmology as a substitute for physics. It's not the same thing. So cosmological redshift, microwave background radiation, arrow of time, these are physical phenomena. We shouldn't say the explanation of these is cosmology. The explanation of those somewhere is physics. Maybe cosmology will come from it, but cosmology is not the explanation. Because if you make cosmology the explanation, you're just making physics archaeology. So it just becomes, yes, the Babylonians, then the Greeks, then the Romans, and so forth. It's just the order of what happened. It's not actually explanation. It's just archaeology. We need a fundamental explanation of physical phenomena in terms of fundamental laws. And it seems to me that the key evidence must be the redshift. If the interpretation of that's wrong, then there's nothing to support the model. That's the only really key evidence. And I've always pointed to the parallel with Kelvin's age of the Earth calculation of 1862. Kelvin, the great Lord Kelvin, said the inexorable laws of thermodynamics said the Earth can only be 20 million years old, because thermodynamics says it would have lost all its heat by then. And geology and biology couldn't fit into this timetable, so Kelvin said, so much the worse for geology and biology, they're wrong. I am right, you're wrong. So throughout your biology, throughout your geology, physics determines it all. There were some people who said, no, you're not right, but how could they challenge Kelvin? But there was something missing, something totally unexpected that nobody knew anything about, and this was radioactivity, discovered in 1896 and proposed as the internal heat source in 1904. Now, could there be something missing in cosmology? That's the question. Could we find something that we haven't seen? Now, I have no objection to anybody putting forward a speculative cosmology. So I'm perfectly happy for people to put forward ideas like the Big Bang Theory and try to make them fit. That's perfectly okay. Nothing wrong with that. That's proper procedure in some ways. But to say that it is a standard model on the level of particle physics is not valid. And then vilifying anybody who says, look, I don't really think you're right about this. This is politics. And as we've seen, it's happened before. Continental drift was another example. So cosmology often seeks superficial answers to fundamental problems. And this is why it's ad hoc. It'll just go for the nearest bolt-on it can get. And that's not good enough. It's no use asking for the answers from cosmology from within cosmology. We have to go from them physics. Now, this is Rogero's way of looking at it. And he goes from mathematics even, and this is his iso-dual mathematics. And following that, I won't go over this because I think you've done lectures on this already, haven't you?
Not on untitled matter today, no, just no untitled matter.
Well, I won't be mentioning much about that.
It's okay, we are free.
So I'll just passed by this quickly, but I want to mention the Minkowski space-time element with the new isodual unit, the isotopic element T in it, which then becomes this. This is for a Minkowski space-time in a medium, in an extended object. Possibly we should consider space to be a medium in this way. Certainly other things are. By the way, you might be very interested in what I intend to show there, because this is, I'm saying that you can actually represent this, as I've done in other things, in nilpotent form. You see, this is a nilpotent form of it. And the reason why you can always represent it in this form is because the only things that are preserved are these algebraic objects here. As long as you've got those unchanged, you can put anything you like in there. And then it must square to 0. So this is a new way of looking at it you might find useful. And this here is an energy, momentum, mass version of it. This is how I would write, if we didn't have the N1, the N's in it, it would be how I would write Einstein's energy momentum equation. And this is how it would be quantized to an operator. So you could get an iso-nilpotent operator for quantum mechanics. And you can put anything in here. You can change these to iso differentials. Anything in there, it doesn't matter. What matters, it doesn't matter from the point of view of getting it to be nilpotent. What matters is that these operators are preserved and anything can be after them. And still, as long as that then fulfills the nilpotent conditions. So the expressions include plus and minus energy, matter and antimatter, two directions of time, matter and vacuum. Now, I think there's a great opportunity here, which I haven't started looking at in any way. I've only actually written down the operators, but I think these operators can actually be extended immensely. Well, one can begin to think about how to use that, because it's a very powerful technique that I've used in other areas. And as I say, I haven't really begun to think about that. Nilpotent, by the way, to me, is a concept that exists to represent self-organization. What happens is that the thing inside the bracket determines everything else. This determines the rest of the universe. Once you've done that, that's whatever's within your system, and the rest of the universe is designed to be effectively a mirror image of that. So you've completely decided your whole system and everything else at the same time by doing that. And this is a way of describing self-organization of any object. And just as a sort of amusing aside, but I think this might be of some interest to Stein Johansson, who isn't with us on this meeting, but if you can use it for biology, you can use it for mathematics, and I've done various versions. I'm sorry, I've lost that. Put that back on. Is that okay? No, it's the other way. Okay. And if one defines a pure unit of this, interestingly, you get an interesting value for your C. If you believe in the holographic principle that everything comes from the bounding area and it can be defined by two spaces or space and time, your C squared becomes the golden section. So this is a new version of your velocity of light here. And I think this relates interestingly to Johansson's derivation of natural numbers from Fibonacci numbers. And I think it also relates to the idea of defining T and I as inverse operators. Okay, this is the mass energy that comes from the ISO theory and the Doppler shift. And then, of course, you've done all this already, so I'm going to go through that quickly. The ISO redshift. So This does not at all prove that the cosmological redshift is not a Doppler. It doesn't prove that. What it says is that there's another reason why one could have redshift. I think you still have to establish whether this is a dominant thing in the universe. And it could be, but we don't know yet. But it certainly is a significant contributor. If one can explain that the redshift isn't a Doppler expansion, then obviously there are going to be major problems for the Big Bang theory. The whole apparatus will have no longer any secure foundation. So we will then have to look for physics explanations, and I suggest we do that anyway. I think that's what you said in one of your papers, Regina, but we don't know whether that's true yet. Also, the dark matter of rotation curves, there was a presenter at the San Marino workshop, De Souza, who suggested that it could be from growing galaxies rather than contracting ones. But however, and Leong, who's here, has said that nuclear reactions in stars may be responsible for cosmological redshift, and got a good value for the value of H from that. And as Edison said, that 3.2 can be calculated from starlight. Now, starlight ultimately comes from nuclear processes. They could be connected in some fundamental way. And the coincidence wouldn't then be a coincidence at all. Interestingly, Hoyle had pointed out that the energy density of the galactic magnetic field, cosmic rays, starlight, and the cosmic microwave background radiation all had approximately the same value, which suggests there may be an equilibrium steady-state process going on there. Now, I haven't said a lot about my own work apart from the nilpotent representation. I'm going to say something that I abbreviate something that I did at San Marino, and anybody who wants the full details can read the paper from that. I think we need to find explanations for fundamental phenomena that are firmly rooted in mathematics and physics, and not tied to an arbitrary and ad hoc cosmology, which then has no fundamental explanation. If you do the mathematics and physics, and then you say, this looks like it can explain the cosmology we've been developing, then fine. I wouldn't have any argument with that. So a theory of gravity and inertia, which I've previously presented, involves the generation of a medium or vacuum structure and leads to explanations of redshift and other things. And I would be very interested to see how much iso redshift would affect this by determining perhaps different values for some of the parameters. Okay, this way of thinking starts from what I said at the beginning of this talk about the Newtonian gravity. Even before I'd actually looked at how Newton did it, I wanted to find a way that was closer to the Newtonian method and not so ad hoc, not so, we'll just make space curved and that will do. No, that's not good enough. I've got to have something that fits in with the standard way of thinking in physics. And it seems to me that gravity gauge theory correspondence, which is something that string theorists talk a lot about, but it existed in my work long before that. It's effectively saying that gravity is a kind of summation of the rest of the forces. Gravity's effect is that of all the other forces put together. And to me, that suggests that gravity is, as I worked out from the quantum mechanics I've done, inside the nilpotent bracket you've got locality, outside of it you've got non-locality. Every interaction, everything that happens has a local part and a non-local part. So you can do it non-locally totally, or you can do it locally. And my idea was that gravity was the non-local part of the summation. And that would explain why it's so weak. And it would also make it instantaneous. We don't know yet what speed gravity travels at. No experiment has been conclusive on this. Measurement certainly requires local interactions at something like c, which is also affected by gravity, as we've seen. If we now incorporate this into Newtonian gravity, we get a version of general relativity in which the C effects are not intrinsic to gravity, but part of our observation system. And that changes the nature of our interpretation of general relativity, though we would still get the same mathematical results. However, what we would get is things like aberration effects, something like fictitious forces, centrifugal force, Coriolis force, and that kind of thing, which could be written in the form of gravito-magnetic Maxwell equations. And I've actually written all these equations out, but I'm not going to do them today. And we can identify the centrifugal component through an argument involving Mach's principle. Now, this calculation I did was done long before the discovery of dark energy, 20 years before. I would not have made so much of it if it weren't predictive. Because it's predictive, that means that you've got more justification in making something of it. But it produced a derivation of Hubble redshift which had no specific connection to any cosmology, but it predicted an acceleration term of the same force and a similar size to that was later found in 1999. And I have subsequently invoked the Coriolis component as the possible explanation of dark matter, the pioneer anomaly, and such like things. Now, let's do the Mach's principle argument. This is the only one I'm going to do in any detail. This says that the inertia of a body, its mass or resistance to accelerated motion, is somehow determined by the interaction of everything else in the universe. And it's long been recognized this must come from the magnetic component. Now, I haven't derived this here, but have derived it elsewhere. If one were to propose such an argument, you would need something like the inductive force. You'd need a gravitational version of that. But this would not be an intrinsic force to gravity. This would be an observational force, one due to the fact that we observed a non-local force by using local interactions. That would be completely parallel to an electromagnetic one. Now, Sharma considered such a force in explaining Mach's principle. But, however, his model used a real such force. He believed there might be a real one. And then he was able to attribute the inertia of a body to the total mass within the observable universe. And if we specify radius, the Hubble radius, RU, and then you make an inductive force equation where you get F equals kma, and you relate k to 1, and you get F equals ma. Now, if we make an additional supposition that the continuous mass field we need for this provides a standard for defining unit inertial mass, just the same as we use the gravitational field at the Earth's surface for defining our own kilogram unit mass. So we imagine that the mass inside the Hubble radius, whatever that may be, defines a radial inertial field of constant magnitude. And this is from a center of a local coordinate system. And we relate this to the non-local gravitational field, then we will get the equation at the bottom of the page. If we make it isotropic to remove the angular dependence, then we will get that equation. And this is what I did in the 1970s. And effectively, one gets the acceleration equals that term. The velocity, when you integrate it, equals h naught r, and therefore you get the Hubble expansion, but you also get an acceleration term. And at the time, I wasn't that interested a bit in the acceleration term, though I thought this might be observed sometime. So this acceleration would be a fictitious one in this explanation. It would describe the effects on the coordinate system produced by using a 4D spacetime to model an instantaneous interaction. So we would have two forces, gravity and the fictitious inertial repulsion, and combining them we would get something like that. And relating them to standard ways of describing things, we would get a Poisson-type equation and a vacuum density of that form equivalent to a so-called dark energy or negative pressure of that form. And because it's an inertial repulsion, it would be an exerted outside away repulsive. We'd get a cosmological constant of that form, and we would get a vacuum density which was 2/3 of the critical density. which is very interesting because the current belief is that it's something like 70, 72 maybe as high as 74, but certainly something around about 70. This would be 67. So you've got a force law, which is a kind of linear expansion with distance, a sort of Hooke's law force, exactly as assumed in dark energy calculations. And it has the classic form of a centrifugal force. And as I say, these calculations are old ones. They were done long before anybody discovered dark energy. So imagine my surprise when they did. Now, I'm going to present a very abbreviated argument. That's the only one I can really claim great authority for because it was done before the experiment. This is done afterwards, so I then say, and I've abbreviated it massively because we don't have a lot of time. I'm going to say that if one considered a kind of accelerating virtual vacuum charges would radiate according to a Larmor formula or something like that, and I would, doing a few more calculations, I would get an equation like the one below, and I then could use that to estimate various parameters, Hubble radius, Hubble time, and so forth. Now, this Hubble radius and Hubble time wouldn't be anything to do with cosmology. They would simply be describing inertial process. They're not that far away from the accepted values for Hubble radius and Hubble time, and I would be very interested to see if ISO redshift would make them give better agreement. Now, the main purpose of these arguments isn't to show that cosmology is incorrect. I don't intend to do that. Even if what I say is true, one could still say, yes, well, that then leads to a cosmology in which you get expansion. People could argue that. I don't wish to argue one way or the other about that. I want to say that the main purpose is to show that physics can explain these things and that we don't need cosmology to explain them. And we shouldn't do, because fundamental phenomena should be explained by physics, and then cosmology should follow. That's the way it should work. So even if we suggest a cosmology from them, it's the physics explanation that is the primary one. Cosmology isn't an explanation, it's simply description. It's a story. Physics is the explanation. And so that's where I want to leave it. Okay, thank you.
Thank you, Professor Rowlands. There is some time for questions, and we start by Professor Corda.
Professor Rowlands, I've seen that you used the equivalence principle was time,
Yes.
but in my opinion you violated it various times. Because in my opinion, in your discussion, you violated the equivalence principle you violate the equivalence principle various times. For example, you claim that there is not curvature. But in a flat space, this implies that the gravitational motion cannot be geodesic, because in a flat space, the geodesic motion is straight. We see that the planet do not make a straight motion. The ballets do not make a straight motion.
That's true, they don't. I know they don't.
If the space is flat, the geodesic motion is straight. Hence, the gravitational motion cannot be geodesic.
Yeah, what we see, you're saying what we see. But one can say that if one were imagining the perfect conditions in which one could describe this mathematically as it so-called really happens, then it would not be what we see. We would see something different. That's the argument.
My point is, in your description, the gravitational motion is geodetic or it is not geodetic?
It depends what your geodesic means. Does it mean as according to coordinates of observation, or does it mean according to coordinates, abstract coordinates of a certain mathematical property?
You are claiming that the gravitational motion is not geodesic.
I'm claiming that you've got two different versions of what you mean by geodesic. You can either mean following coordinates as observed, or you can mean following some abstract coordinates which you lay down. I'm saying that's what Newton did. He had his geodesic was a elliptical orbit, but that elliptical orbit was never observed because it was in an abstract coordinate system which you didn't observe.
Okay, in the local reference frames of art, the gravitational motion is geodetic or not geodetic? In your theory, we are in respect to the sun. We are in a local inertial frame. In this frame, the gravitational motion is geodesic or not?
Oh, I think it's geodesic, yes.
If it is geodesic, the space cannot be flat.
The coordinate system isn't, but the space...
Repeat again, Professor Corey. If it is geodesic,
The space cannot be flat because it cannot be flat. Cannot be flat.
Well, no, your coordinate system
No,
isn't. flat.
absolutely.
Your coordinate system isn't, but your space is. That's a different thing.
The coordinate system is not flat.
The coordinate system isn't, no.
Okay. This is.
But it isn't in Newtonian theory. The coordinate system isn't flat in Newtonian theory.
The coordinate system.
Yeah, he doesn't use flat coordinates because he uses
It's not
special
flat.
coordinates in which he can preserve elliptical motion.
Okay, you are knowing that the coordinate system is curved. Okay, you are saying maybe we are saying the same thing.
I think
but
we're talking at cross purposes because I'm saying that coordinate system and space are different concepts.
on the other hand, when you use as you divide the gravitational interaction, a part inertial, a part on acceleration.
Yes, but the other part's inertia. There's inertia and gravity.
This also violates equivalence principle. Equivalence principle implies that the
Yeah,
gravitational.
I don't think the strong equivalence principle is correct because the strong equivalence principle, the strong version of the equivalence principle, I don't think is correct because the strong, and nor does general relativity doesn't preserve it either. The strong.
No, also the Norton theory preserves the strong equivalence principle.
Well, he
Baryometric theory preserves
but
it.
the strong equivalence principle, I don't think is correct because.
Why?
Because it is saying that inertia is the same as gravity, not that gravity causes inertia, which is what I'm saying.
Gravity?
Causes inertia. Gravity it causes inertia, but inertia is not the same as gravity. So if gravity weren't there, then that inertia
the
wouldn't happen.
equivalence between inertial mass and gravitational mass is tested at a level 10 to minus
That's the
13.
weak equivalence principle. It's not the strong equivalence principle.
But this, no, strong, okay, the stronger.
I don't accept the strong equivalence principle. I accept the weak one.
Okay, this is clear.
Yeah.
No, vabbè, okay.
First, our colleague here.
You have said that there is no significant difference between Newton's formalism as expressed in Principia and the curvature of space in general relativity. And
There needn't be. I mean, there is because he doesn't bring the velocity of light into it. But he could have done without grossly violating what he did.
in your third or fourth slide, you had mentioned that the Newtonian formalism is
I think it's the same
Yes.
sort of thing.
Yeah.
I don't think it's the same.
quite.
I don't think it's the same. I think it's the same sort of way of thinking. But I don't think it's the same actual information.
I would appreciate if you could explain how that formalism can explain the bending of light while it passes through the sun, quite close to the sun.
Right. Do you want me to do that on the board? Sorry.
I was supposed to go into the same direction with respect to the bending of light, but please.
Okay, you've got a hyperbolic orbit. Okay? Hyperbolic orbit, because light's very fast. Now, if you've got, he believes that light is a particle, and it's traveling very fast. Now, you've got two choices. You've got that's your gravitational potential energy. And you've got, let's see, I think it's this way around. I think it's either E plus 1 or E minus 1 because it's a hyperbolic orbit. So you've got an eccentricity term. Okay? Now, what have you got on this side? You've got two choices. Right? You've got half mv squared, or you've got mv squared. Is the orbit already in existence, or is the light dragged into orbit when it comes? Now, when, what's the name of the man? Soldner did this in 1801. Effectively, he chose this because he thought it was the reverse of black holes and escape velocity. When Eddington did it in 1919, he did that. So he got a value that was the wrong value. Now, Soldner only got the wrong value because he didn't double his integral, because he didn't do in and out. But you see, if you choose that value, you get 1 over e basically, because e is very big. So 1 over e equals 2gm over rc squared. So that's the eccentricity, and that's basically your delta. And you take 2 delta because it's in and out. And so you get 4gm over rc squared. So you can do it by Newtonian theory if you make certain assumptions. It's not completely divorced from it. People often think it's completely something very strange, but it's basically just another Newtonian type of theory.
Professor, excuse me.
No, the Doppler shift is trivial. That one's even more trivial, but you've got to assume quantum theory is true. You've got to assume quantum theory. Okay. And sorry, minus h nu. And so you do, let's get it right. Yeah, GMM over O minus h nu. And when you sorry, I've got this wrong. It's h nu minus GM over R, the wrong way around. H nu minus GM over R, and the m is h nu over c squared. That's the little m. That's the gravitational potential. And so that becomes h nu 1 minus GM over RC squared. So that's a trivial one.
And what about the perturbation in the orbit of Mercury?
Well, that's more difficult.
Yeah.
That's more difficult, but it can be done. What you can do is, you can do it by special relativity. That's one way. Or you can do it by, I think actually if I go, as it happens on this, because I was working on some things, I may have a slide on it, if I do it quickly enough. This is something else, this isn't this presentation, but I may have it on here, I may not, I'll have to see if it's on here. That one. See that slide there? This is a standard ray, a light ray. This is a light ray without any gravitational potential. This is standard, this is a standard light ray geodesic with a gravitational potential. That's a standard orbit. This is a deflected orbit. Now, if your observation is through that light ray, is through light, or anything that depends on the velocity of light, then in fact what you're doing really is putting gravitational potential on this. You're putting a standard Newtonian term onto there. So the gravitational bit is purely Newtonian. And the bending of light bit, which we've already shown, is the bit there. So you can put, it's not the correct way of doing it, but it's a way that gives you the idea of what happens. But there are lots of ways of doing it. All these things can be done. People say it can't, but it can. There's not one of those concepts that can't be done by some sort of Newtonian method. As long as you make certain assumptions, quantum theory, velocity of light, and so forth. Yeah, you've got to make some assumptions. But you don't need esoteric methods to do any of them.
Okay, just, excuse me.
Yeah.
Please, just a first order.
Yeah, subquantum kinetics also talks about flat space.
Yes.
And there, a light ray would diffract or refract
Okay.
around the
Yes,
sun.
certainly, that's a way of
where
talking
the
about it.
velocity of light changes is changed by gravity. So the light wave is going slower on the side towards the sun, and you get the exact same results. Just related to your comment, being the spokesman for subquantum kinetics, I would say it fits your concept that you begin with physics and extrapolate to cosmology, because you're beginning with those sets of equations, and from that you get that the space should be subcritical, and you should get a redshift, and you also get this continuous creation happening. So you get all of these coming out of where you start, out of the unified field theory.
Okay, thank you, Professor Santilli. Comments?
Thank you, Professor Rowland. It's always a pleasure to listen to your lecture. A little bit of envy, because you have such a nice presentation, you demolish theory in a very nice way. I'm brutal by comparison. Yeah. Thank you. It's appreciated, your style. A comment, only a comment, regarding the isoredshift shift. To the best of my knowledge, at this moment, the isoredshift shift combined with Zwicky hypothesis that light loses energy in the long travel to Earth, that's why it's called the Zwicky-Santilli effect, does represent...
Combined with Zwicky.
Yes.
Combined with...
But no, but it's the same principle. The principle of the isoredshift shift is that it's a geometric principle, as well as interaction between light and matter. When light is very cold, you need energy for the interaction. The atoms cannot provide the energy, so necessarily the energy for interaction has to be provided by light when the medium is very cold. Yeah. And therefore, light loses energy. This is isominkowskian geometry. Loses energy in the travel through matter. Yeah. But Zwicky, 1929. Yeah. So the principle of light losing energy to the medium is not mine, belongs to Zwicky. Yeah. That's why it's called the Zwicky. Now, back to the point, to the best of my knowledge, this, let's call it a Zwicky-Santilli effect, represent exactly all experimental data on the cosmological redshift better than the expansion. Let me elaborate. This is not, because before you, when you arrived, before you, there was a talk by Professor Laviolette. In 1986, he published a paper on the Astrophysics Journal in which he showed that the principle, the Zwicky principle, namely light losing energy, fits experimental data on the cosmological redshift better. He showed many diagrams. It's a beautiful lecture. Many diagrams, better than the expansion. So at this moment, to the best of my knowledge, could be proven wrong. My God, we could be proven wrong. To the best of my knowledge, the redshift, let's call it the Zwicky-Santilli effect. Light loses energy to the medium. That's what I only provide.
Yeah, but couldn't you say what I was saying is a Zwicky effect?
I'm sorry?
Couldn't you say what I was saying is also a Zwicky effect?
What? I missed the point.
My argument about that produced this redshift acceleration thing, could you not say that was also a Zwicky type concept?
What is a Zwicky time? Completely unknown.
Zwicky.
Oh, Zwicky. It is 100% Zwicky.
What I was doing also is similar.
Oh, yes. Oh, my God. Nature is polyhedric. For every physical, in other words, once we admit the basic physical principle, but again, what our group has done has provided mathematically rigorous geometric derivation from first principle with the symmetry, providing the same number and the same condition at different times, and above all, years and years of measurements on Earth, as Galileo said. But back to this, once this principle is established, at least admitted, according to current, namely light loses energy to the medium, then Professor Rowland, nature is polyhedric. There will be many different models that will...
I'm saying many models will do it.
Yes, yes, but...
they're not necessarily contradictory. Many of
no, they're complementary. No, your view is complementary, absolutely, no contradiction, provided the basic physical law is verified. So to the best of my knowledge, now this is the situation. Unless there are counter-experiments disproving on Earth, that indeed light does not lose energy in a physical medium. I think this will be impossible because many years and years of measurements everywhere, confirmed here, now redone independently in various countries, so I think it will be difficult to disprove. I have only, regarding your lecture, I have only one point regarding one comment, and I don't want to take because we have the next otherwise we'll discuss it privately. Yeah. Okay. You mentioned regarding in the Big Bang, that of course I do not believe. I had irreconcilable disagreement with my colleague at Harvard. regarding the Big Bang, because it's an explosion, and the universe, galactic environment around the Earth should have been empty for 13.7 billion years, totally empty by the explosion, etc., etc. The point is this: you mentioned that there is no connection between the cosmological, the cosmic background radiation and redshift
In the Big Bang model.
in the Big Bang model. Yes, correct.
There's no good one.
Yes.
There's no very strong one.
I agree. However, there's been graduate students years ago that proved that since it's very weak, the cosmic background radiation should have been absorbed by galaxy. I don't remember how much, 3 or 4 billion years ago. Yeah. So to have a credible, plausible model, the background, cosmic background radiation, in my opinion, I agree with that paper. Cosmic is not mine. The cosmic background radiation needs a continuous source of energy. Right. The best is the Zwicky-Santil effect. That energy lost by light to the medium cannot be lost. And apparently, essentially, technically, it's absorbed by the hydrogen atom in the intergalactic space. And then they release it precisely on that frequency of the background radiation. And it provides a continuous source of energy. So in this case, there is a direct numerical, quantitative connection between the cosmic background and the origin.
That's also what I'm saying.
Yeah, okay.
That was also what I was saying.
Yes.
Because if you've got accelerating sources, they're effectively radiating, and they're radiating this energy into the cosmic background. That's what I was saying.
Yes, it's another
interpretation.
Yes. But now we are going down to quantitative, no more philosophy, no more theology. We go experiment.
Yeah, we need physics, yeah.
Physics, that's what you said. Beautiful. Yeah. You said it very, very nice. Physics in background.
And if the cosmology then follows the physics, fine.
Please, time for one question more.
I would like to comment after that. I forgot an important point.
Small question. Do you know that hydrogen atoms has noise, and this noise...
Hydrogen atoms have noise, he said.
Noise, this temperature parameter of this noise, electronic noise, the same as a cosmic microwave background.
Well, that wouldn't surprise me, because that would fit in with what Hoyle said about all these different processes having the same energy density. So what he was saying is that the starlight, magnetic field, cosmic rays, and background radiation have the same energy density. So if you're saying also hydrogen, then that would fit in with an equilibrium process, because that would come to a constant energy density which would determine all those processes. So I would think that would fit in with that.
I talked about it at the conference and show
well, we talk about it later.
Formula and all parameters, and I don't want to repeat again the same.
You can give me a copy of your paper.
Question, because, okay.
Please, Professor Santilli, the next comment.
Very quickly. Professor Rowlands, you mentioned this your very elegant language. There has to be, namely that prize, for the Big Bang was done a couple of years after. Yeah. I was an eyewitness in what is called the Nobel Prize Factory in America. That's Cambridge. I was MIT and Harvard. I witnessed the organization for that prize. I think we have to, because if we don't disclose the situation, we become servant, as I said before. What happened was the following: that the steady state was, as he correctly said, was becoming dominant. But the steady state implies always that everything is happening in the scientific politics. Einstein would have implied that the redshift, the interpretation of the redshift would have violated Einstein's special relativity. That's exactly the case of isoredshift. Now, the academia at that time did not want that. So that is why it was organized prize to impose the Big Bang by academic power. I already know the mechanism. They selected 100 major scientists all over the world, And this 100 scientists wrote a very, very strong letter of recommendation to the Nobel Committee. This has happened systematically when there were in other fields. Whenever there is doubt on Einstein, immediately you see a Nobel Prize. You see this happened for it happened again for the neutrino. There were doubts on the existence of the neutrino. 1 or 2 years later, 100, 150, there was an organization, 150 top physicists, and the Nobel Prize granted the Nobel Prize. It goes on and on. I have to voice my extreme reservation on the Nobel Prize committee because they are supposed to be made of physicists capable of judging if a theory, if this type of collegiate proposal are just an organized political structure, or they have an intrinsic fact.
Mean, they did make a discovery, these guys. It's just it was so quick. It was intended to.
But the discovery was questionable. It's like the latest Nobel Prize per Mutter on the expansion of the universe and the dark matter was exactly the same. Since now, this was after the experiment of the ISO redshift that casts doubt on the whole thing. Immediately, 150 top scientists all over the world have sent a letter to the Nobel Committee, immediately a Nobel Prize to maintain the acceleration of this. This has been systematic.
But there is a cosmic microwave background radiation.
I'm sorry?
There is a cosmic microwave background radiation.
But
there is such a phenomenon.
No, but the Nobel Prize per Mutter was granted on the acceleration.
No, I'm talking about that. But Penzias and Wilson did discover something.
Yeah, but it was the interpretation.
No, there is argument that they weren't the first.
French astronomers.
Possibly, yeah. It could be, yeah.
Okay. Any other comment? Thank you very much, Professor Rowlands.